today's lecture is going to be about file input and output, text-based, throwing and generating your own exceptions as well as handling those exceptions. And finally, we'll finish up by talking about unit testing. Doesn't seem like these things are related to each other, but they are. And they're all really small topics. In fact, today's lecture will be quite short. Okay. So, first of all, let's talk about file input and output. Again, we're going to be focusing on text input and output. Binary input and output is pretty similar, but that's something that you'll address in a later course. So for now, anyway, just the basics of reading a text file and writing out data to a text file in a couple different popular formats. So there is an open function in Python, and it takes two arguments. The first is the path name, or the file name. Excuse me. And it can be a relative path relative to the working directory, or it can be an absolute path, which includes all the paths up to that file. You do have to be careful. In some situations, the working directory doesn't match the directory where the file is located. So that's one thing that you do need to be aware of. I'll address this when we do the demo so that we can get a feel for it, because in Visual Studio Code, sometimes it's in the same folder and sometimes it's not, depending on what folder you have open in VS Code. And a lot of other IDEs kind of work the same way. Often there are many that will literally never use the directory where the source code file is located because of how the development environment works. So the first argument is the path. In this case, I only have the file name, the data file name, because I'm assuming this is in whatever the working directory is. The second argument is going to reference whether or not we're going to be reading or writing the file. We can also append to an existing file, which is like writing, obviously, but instead of writing the existing file, it adds new data to the end of it. All right, some other functions that we might want to use is file.read. This is used all the time because this is very handy. It reads all of the file. So especially for a text file, then the results of this file.read will be a single string that contains the whole contents of that file. So that's pretty helpful. The read function is also for a binary file. You can also use it to read individual chunks of data. So you can specify how many bytes you want to read, for example. So you can see that version down here. There's also a seek. This is really used for binary files usually, especially really large ones, where you have something like, I don't know, customer database or something like that. If you're implementing your own database management system, then seek will actually jump to a specific byte somewhere in the file. The file is quite large, so you don't want to read the whole thing sequentially. Using file.read, you want to read just a little bit that you want, so you can seek. So in this case, these two can be used together. We can seek to the 10th character or byte. It's index 10, and then you can read 5 bytes at that location. You can use these with text files, character files, but generally speaking, we usually use these in binary because it's usually used in combination when we have a huge file. So we use binary for compactness, and then the binary file also has a lot of data in it, and then you can jump to the specific location. You can also read just a line. It'll read until it finds the first new line character. So that's a possibility as well. All right, so here's an example of how I could use the open function appropriately. So here I call open. You can see I pass it a file name, and I'm saying I want to read the file. And the result of the open function is an object in Python that represents the contents of the file. It actually isn't the contents of the file. It's just sort of a handle to the file, and that allows you to request the data from the operating system when you do need it. So it doesn't load all the data until you ask it to, but basically it represents an open file. Now, one thing I want to note is that an open file is a resource that your operating system tracks. And if you keep the file open, then you can have a lot of open files that can have a negative impact on the performance of your operating system. So as a programmer, you have a responsibility to close the file when you're done. So here you can see at the end of this little code snippet here, I say file.close. That explicitly closes the file. For read files, closing is important, but for write files, it's critical. And people often forget how to do this, forget to do this at the end of their program. It's very easy to forget. And so there actually is a construct in Python created specifically to solve this problem. But anyway, let's go over the snippet of code before we go on to that. So after we open the file, then what we can do is we can actually do for variable in, and then this is the file handle that we got as return value for open. And what this will do is this will automatically call file.readLine. It's going to read one line, including the new line character, and then it'll print that to the console. So just note one consequence of this is that this print is going to put a new line at the end, and the line string itself has a new line character at the end. So there'll be two new lines at the end of each line. Okay, so here is the better way to do it. This is what I would recommend that you do for all of your input and output uses. So in this case, and that includes, by the way, things other than files. So we use this same strategy. For example, if I wanted to connect to a web server and I want to make sure I disconnect from that web server, that actually has an even greater negative impact on the performance of your computer. If you don't close those sockets, sometimes they don't get closed right away. And Python does have garbage collection where it deletes files that it doesn't need anymore, and deletes objects that it doesn't need anymore. And if one of those objects is a file handle, the file handle will close the corresponding file that it represents. But that doesn't usually happen right away. So for efficiency reasons, Python will wait to garbage collect things much, much later. And it also has to be absolutely sure you're never going to use that object again. And so it takes sometimes a long time. And so leaving these files kind of dangling open, especially if your program is going to run on a continuous basis. For example, let's say I'm writing a malware scanner. It's going to be running basically the whole time your computer is on. Then it's really important to close these files. You can see the code inside here is exactly the same. So the only thing that's different is this very first line. You can see we're still calling open. We still pass it the same file name. We still pass it R for the read mode. But in this case, we're saying with value as variable name. So instead of saying variable name equals value, so instead of saying file equals open data.txt, R, we're saying with open data.txt, R as file. So it's effectively very, very similar in operation. It's going to create a file variable, and the file variable is going to contain the result of calling this open function. But inside the indented portion of this with clause, the file variable exists. As soon as we exit this with clause, the file variable will be marked for deletion, and it will be garbage collected. And as I said before, Python will automatically close the file when it garbage collects the object, the file handle object. So this is actually the preferred way to open files, whether for reading or writing, whether for text or binary, and use a similar technique for connecting to network programs. A lot of other input and output things should use the with clause instead of the code on the previous slide. So writing files are pretty similar. So we're going to use the with clause from here on out, so I won't be using the other syntax anymore. So here I just have an array of numbers, and I use with open. This time you can see that the second argument to open is a W, meaning to write. This is going to erase any file called data.txt and overwrite it with a new file. Now here I'm using the exact same variable for the file handle, file. And then what I do is I loop over the items list, and I write each one. And I'm kind of using an old syntax here instead of an F string because I wrote this code a long time ago. But I convert the numeric item to a string, and I put a new line at the end because write, unlike print, doesn't automatically add a new line at the end, so you have to manually do that. So I'm just concatenating a new line string to the end of it. But anyway, this will do the function. And you can do the exact same thing with an F string, of course. So one of the file types that I might want to export is called JSON, and JSON is short for JavaScript Object Notation, which is kind of weird because we're learning about Python, but JavaScript Object Notation originates from JavaScript. And so basically it uses a notation that is similar to, not quite exactly the same as what JavaScript uses. So if you have a list of things, the list uses square brackets, which happens to be what JavaScript uses for its lists. And if you have a string, it uses single quotes and double quotes, which happens to be what JavaScript uses. But in JSON, it's preferred if you use double quotes as opposed to single quotes. And similarly to Python, Actually, so far, a lot of the stuff is the same in Python. But similar to Python, there's also dictionaries in JavaScript, and they work by using curly brackets. You can see an example here. And then we have the name of the field, colon, and then the value. And the value can be a different type. For example, you can have integer types, floating point, string. In this case, you can see one of them is a list of string. All right, so one of the things about JavaScript object notation is that values are usually strings or list of strings or dictionaries. Okay, so they aren't typically integers and so on. And I think there are some JSON libraries that will support integers and floating points and stuff. But to make sure that you're compatible with everything, it is commonly used, the practice is commonly used that we just put everything in quotes to make it a string. So you can see here the grades are actually strings, but they do contain what appears to be floating point values. And similarly, the SID, the student ID, here is an integer, but I've decided to make it a quoted string, even though what's inside looks like an integer. So this is a useful format. It's used for so many things. It's often used for things like configuration files. So if you're writing a program and you want to store, the user's preferences, their font size, and whatever else, their zoom level that they're using. Say you're creating a browser, all their bookmarks and stuff. You can save all that stuff in a JSON file or maybe multiple JSON files. So that's commonly used. And if you access a web API, for example, if you want to query Instagram and you want to say, give me all the Instagram posts by this particular user, the result that you get back will be in JSON as well. And there are a lot of open data portals that you can find, like Government of Canada and various state and provincial governments and municipal governments and so on will usually export some of their data to the public that you can use generally. And one of the formats that's commonly used for these sorts of things is JSON. And there are APIs dedicated specifically for performing tasks for you, like software as a service. So for example, converting between currencies, finding stock prices, getting Bitcoin prices, etc. Those can all be done using APIs that, of course, use JSON as their format. So when you request Bitcoin prices, it'll give you back a response that'll say what the Bitcoin price is, what time, and so on in various currencies in JSON format. So it is a really widely used format, probably the most widely used text format on the web. So I think it's pretty important to know how to use it. So what if I want to read in a JSON file? Well, we're going to use a library. It's not built into the main Python language, so you have to import a library called JSON. But JSON is included by default in Python installation, so you should already have it on your system. And then we can use the open function that we just saw. Just notice that we have a .json extension. That's not required. You can call the extension whatever you want. But at least if you do say .json and you open it up in a text editor, the text editor will use appropriate syntax highlighting for a JSON file. So anyway, so that's that. So this is basically the same as what we've seen so far. But instead of loading the file using something like file.read, which will just read the text content of it, we can do json.load. There's a load function in this JSON library. Because we just said import JSON, we need the JSON prefix here. There's a load function here. And we just pass it the file handle, and it'll read all the text from that file, process it as JSON, and convert it into a Python object. So imagine that JSON file has a dictionary in it, like the sample that we saw. Then Carla here will contain a Python dictionary. So there's very little difference between a JavaScript dictionary to a Python dictionary, but JSON.load here will do any changes necessary. And imagine if the file contains a list, then obviously Carla here will then contain a list of values, a Python list of values, and so on. So it does all the conversions necessary, which is pretty cool. So this is kind of a one-stop shop, pretty easy, single line of code for loading in a JSON file. And then you can also write a JSON file in a very similar way. So here I've got a Python dictionary called Carla. We're just kind of doing the opposite. And I'm just declaring 4 fields in that dictionary and all of the values here. I've made them all strings just to kind of match the version that we saw a couple slides back in the JSON example. But excuse me, but they don't have to be. They can make them other types. This could be grades, which is literally a list of floating point. That would be okay. Anyway, we open the file for writing, and then we just say json.dump. we pass it the thing that we want to export, and then the file handle. So this requires two objects, two arguments being passed. Carla happens to be a dictionary, but it could equally be a list. It could even be a string or just a floating point number. It could be anything as complex or simple as you want. And you might be wondering, well, what happens if the JSON file or my internal Python object is like a dictionary that has a dictionary inside it, or a list of dictionaries, or some complicated combination of types? Those will work perfectly fine. Okay, so it'll load all of those. And of course, it's going to use recursion in order to do that. Okay, so let's move on now to the next topic, which is exceptions. And why is exceptions related to input and output here? Well, file input and output in particular has a lot of things that could go wrong. And it's not always the programmer's fault. Like a lot of the exceptions that we've seen so far have been because exceptions or runtime errors. We've seen examples of that, which are things that we did wrong. Like for example, I used an index that was too big in a list, or I divided by 0, or whatever. Those were my mistakes. And those errors are exceptions. And so students sometimes think that exceptions are just kind of an annoyance. It's not a useful feature. But I hope to change your mind today in that exceptions are actually a useful programming construct. It's not a necessary one because there are lots of programming languages that don't support exceptions. But the ones that do tend to have nice, clean code. So programming languages that don't support exceptions will usually return special placeholder values, or flag values, they sometimes are called. And so they, for example, we might have a function and it will retrieve some value, and it'll return a special value like -1 as an indicator that something went wrong. And that's sloppy because you don't know really the nature of the error. What was the cause? You don't really know. Maybe even -1 is an actual valid value. So exceptions are better because if a function returns a value, that means it successfully did its job, and the value that you've got was the value that was calculated or read from a file or retrieved from the internet or whatever. Exceptions are a different construct, and you can tell the difference when an exception happens. Not only that, but you get some information about the error, where it happened, what kind of error it was. There's a little error message that comes along with it. And you can also have multiple different types of exceptions. So consider this scenario. I'm trying to read in data from a file. And I tried to read in a file, let's say that's in the, let's say a Windows machine. It's in the C Windows directory. So I know in the C Windows directory, there's a file called user.dat. And I try to read that in. Well, one possibility that could go wrong is that file is not readable because the Windows directory might be limited to just the administrator account, and regular users can't use it. And I happen to be running this program right now as a regular user, not an administrator. Another possibility is that file could have been deleted. So maybe it existed at one time and it got deleted, or maybe I just typed the file name wrong. Those are all possibilities. And another thing that can happen is sometimes you think that the current directory is one directory, and it turns out the development environment you're running it in is a different directory, and so it doesn't find the file because it's looking in a different place for that file, so the path is not quite right. So those are all possibilities where it have to do with the file or path name of the file. And so another possibility is that the file was on a USB drive or on a cloud drive, and now that cloud drive is no longer available because of whatever reason. Maybe you timed out and you have to log in again or something. And so in that case, that's another error. So when you're doing a lot of these file reading or writing, a lot of things can go wrong. None of these errors are the programmer's fault. They're really user error, or they're caused by something outside the scope of the programmer. This is running on somebody else's machine, and it works fine if used correctly, but the user has used it incorrectly. Exceptions can be helpful in that context as well. So sometimes the errors are caused by you, and sometimes they're errors that you have to check for because you know that the user is going to cause those errors, or at least there's potential there for them to do that. So anyway, I hope that I've convinced you that exceptions are a useful thing for a programming language to have. Most modern programming languages do have them. Anyway, so they're just runtime errors. We say we raise an exception in Python. In a lot of other programming languages, they say they throw an exception. That just means that we make an exception happen. We basically invoke an exception. So they happen all the time with input and output. Another type of input and output that we'll typically do is socket communication, where we're trying to connect to a network program somewhere else on the internet, and the exception could happen because of all sorts of issues that can go wrong. It could be a routing error, person's Wi-Fi could have gone out, they could have unplugged an Ethernet cable, all kinds of things could happen. Anyway, so what you do basically is you're going to handle these errors, which on some programming languages called catching the error. That kind of pairs with the throwing an error. You throw an exception and then you can catch an exception. So imagine there's a function, for instance, that you're writing. The function might raise or throw an exception, and then the part of the program that's calling that function would catch or handle the exception. Okay. You can also define your own exception. This is really easy to do. I'll show you an example of that. So the first thing let's talk about is how to catch or handle an exception. We're going to use a try except block. In a lot of programming languages, it's called try catch. So we try to do something, and then we catch any errors that may occur. But in Python, it's called try except. And that's actually pretty good. And keep in mind, it's except, not accept, because in this case, what I'm trying to do is I'm trying to do something that potentially could cause an exception, and I just want to do that thing, except in some cases, this exceptional situation might happen. That's where the name comes from. Exceptions are, the rare case. It's not what's supposed to normally happen. So in this case, I try to do something. Let's say, for example, I try to open up a file. And so we've seen code to do that. We call the open function, let's say with R as the mode. And as it turns out, we generate some kind of an error because there's no file with that name. So the except part of the clause, you can see that it has a type, some error. Some error is actually the type. Presumably this is an error that I've made up. It's not a very good name. There are some built-in exceptions. We've already seen index error before. If you try to, if you have two elements in your array and you try to access the element at position 2, well, that's an invalid index because the two elements have index 0 and 1. 2 is not a valid index. So in that case, if you try to access the array square bracket 2, it'll give you an index error. There's also I forget what it's called, 0 divide error, I think it's what it's called. If you try to divide by 0, there's all kinds of errors like this that can happen. Or if you have a variable and you try to call a function on that variable, but it turns out that that variable contains an object that doesn't have that function, that will generate an error. So these are all exceptions that are possible. There's a bunch of built-in ones. But oftentimes you want to create your own. You might have some specific ones that match the situation that you're developing. So imagine, for example, you're trying to write some code to keep track of like GitHub commits. Let's say, for example, you're putting your code in a Git repository on GitHub or GitLab or something along those lines. And let's say, for example, you're not logged in. So you can't obviously push code to a repository if you're not logged in, because the GitHub and GitLab, they have to verify that, in fact, you have the permission to do that. So that might be one kind of error. So you might actually create something like an unauthenticated error or something, your very own exception. That's what it means. Or you might say that you only have read permission on that repository. You don't have write permission on that repository. So there might be another error that says, no write permission or something like that error. So again, you can make your own errors, and they represent situations specific to the problems that you're working on. So this try except is useful in two contexts. One, you're trying to do something, and then you're not creating your own exceptions, but as a result of the thing that you're trying to do in the try block, something could go wrong where the built-in exceptions could happen. So you could be using try except for that. Just one quick note, don't try to cover up your errors. Like if, for example, there's a possibility of divide by 0, don't put try except around it, because if it does happen, it's going to give you a nice error message out in the console anyway. And that error message is going to have the line number, it's going to tell you what kind of error, and it'll give you all the clues you need to solve the error. If you put in a try except block, whatever you put in the except block is only going to happen. And so if you have a print statement that's kind of vague, and it doesn't give you all that information, like this one, for example, it doesn't include the line number where this happened. And if I have a lot of similar except clauses in my program, I might have no idea where this error occurred, and it's harder for me to track down. So it actually, I've done a disservice by putting this try-catch block in there. You only put a try-catch block is not to fix your own bugs. Like during the testing process, when you're fixing the bugs, presumably when you push your code out to production and actual users are using your software, by then it's assumed anyway that you won't have any errors. I mean, they do obviously still linger sometimes, but in that case, then your try-catch blocks are for errors that are outside of your control. They're not by programming errors on your part. They're errors that users have made. So that's why you usually put try except in there. And the reason why you do it, instead of leaving it out, like I was mentioning, if, for example, you were to not put try except block in there, you get a nice error message, the line number, and so on, is instead of like printing something out to the console, you want to present the user with an error message that helps them use your software correctly if they're using it incorrectly. So, for example, if the user tries to access a file and it's not a readable file, if you give them a descriptive enough error message, you pop up a little pop-up dialog saying, yeah, you don't have read permission on that file, that'll help them solve the problem. So they can actually say, oh, okay, I need to log in as administrator and run this program or something, whatever they need to do to solve it. So that's one way that you can use this try except, and then you might also use the try except to catch your problem-specific exceptions. So these are exceptions that you create, and then you use try catch in some other part of the program. When you're trying to do the thing that's going to create that exception, you'll put try except around it, so then you can handle that exception, again, in a user-friendly way. Not a programmer-friendly way. Okay, so if you want to create your own exceptions, well, you can literally just create any kind of subclass of the exception class. Most of the time, you don't need to provide any content of this class because the exception parent class has pretty much everything you need. It basically just includes an error message. And all the errors that are built into Python, they also derive from exception. And so your error will start to behave exactly like the built-in errors will, which is quite nice. So in this case, I've created a class called myCustomError, and it inherits from the exception class. And I just put pass in there because I literally don't have any content. I don't want to change anything out, any arguments or functions, any instance variables or functions or anything like that. You absolutely can, of course, but you typically don't have to. So somewhere else in your program, that's what these ... dots mean here, you're going to have a clause that says something like raise a custom error. And by the way, a constructor or initializer that contains an error message already is present in the parent class exception here. So you can literally just call that. You can literally pass an error message to it when you create the error. So this is going to cause the error to happen. You don't need try except around this raise here because if you want to, this can be inside a function, and then raising an exception inside a function will actually make the caller of the function receive the exception. So it'll kind of jump you right out of the function, which is helpful. Usually when an error like this happens, you want to stop everything and then tell the user what they need to do to fix the problem, and then they go back and try again. All right, anyway, so that's how you can make your own exceptions, and we'll do a demo about that. You probably need to see it in action in order for it to see how it fully fits together. All right, so let's talk about our third topic then. And this one also, believe it or not, is quite closely related to that, although not quite as closely related. I mentioned that exceptions typically happen when you're doing input and output. Of course, file input and output is one of the types of input and output that's very likely to produce exceptions. And so those things go together quite well. You really need to do both. You need to learn both at the same time, I think. But testing is also helpful in this way because you're probably going to write some code and you're going to want to test it. And we're going to talk specifically about a type of testing called unit testing, where you're basically testing your individual classes by themselves and also the functions, maybe the functions within the classes or just functions that are by themselves. So that's called unit testing, and it's a very important type of testing because you're going to test all the individual components. You still need to put all those components together and test them as a whole. That's called black box testing, which is a different thing, and you will learn that at a later point in time during your studies. But unit testing is what we're going to focus on here. It's typically done using code. rather than like manual testing. Manual testing is very tedious. You go back, you fix something, you have to run all those tests again to make sure that what you just did fixed it, and also what you just did didn't break something else. So you have all of these tests to make sure that things are still working. It can be very helpful when you commit your code if you have a huge suite of tests that are going to test to make sure all the functionality that was previously working is continuing to work. And then when you add some new functionality, you create a new suite of tests that are going to test to make sure that that functionality is working exactly as you expect it, even if something weird happens. So on that note, there's a meme here. So here's an example of a quality assurance joke. And so it says, a QA engineer walks into a bar, orders a beer, orders 2 beers, both quite sensible. And then orders 0 beers. I wouldn't really expect anybody to do that. And so the problem is, because you don't expect somebody to do it, you probably didn't write the code to handle that situation. So this 0 beers here, it might fail. Or orders 10 to the exponent 30 beers, orders -1 beers, orders 2.75 beers, orders something that apparently is a memory address beers, and orders a string, a null, this is a null character, orders a gorilla, thing that is not anything. These are other types of objects that shouldn't be supported by the situation. And so if you want to order a beer, it should be a positive integer, right? But you can always count on users using your code incorrectly. And so these are things that QA engineers typically are familiar with. They're trying to test different situations. They tested orders 2 beers. They didn't test orders 3 beers because you wouldn't expect that to work differently. If something is like more than one, you would kind of expect that it would generally work. Except for there's an extreme example here where we're talking about 10 to the 30. That obviously is a huge number. We want to make sure that there's not like overflowy things going on or whatever. So these are all the tests. And then somebody posted a comment saying, customer asks where the bathroom is, and the bar bursts into flames. So not not completely outlandish idea. And so this is something to keep in mind. This is quite clever because this represents a really good set of tests. Okay, now I understand ordering a beer is not something you're to write code for, but this is actually a really good representative example of what a test engineer goes through when they write tests for something. Now, for unit testing, you're the test engineer. Okay, so you don't work for quality assurance. You are a coder, but you're still responsible for writing unit tests for your own code. The quality assurance people will typically do things at a higher scale, like the black box testing. And so they'll do these kinds of tests on a larger scale, which kind of tests like how the whole software system works, all the classes and functions work together. But your job is to make sure that the individual functions and classes do their job as expected on their own. And then the quality assurance team makes sure that when combined together, they still work. Okay. So quality assurance has a whole bunch of different, quality assurance is not just the group who only tests software. Quality assurance is the whole process of making sure that your software is of sufficient quality. So there are 2 kinds of tests. One is the functional kinds of tests, and one are the non-functional. Probably the ones you think of are the functional tests. These are the ones that say, is my software working the way I expected it to be? And that includes unit testing. I mentioned that's testing functions and classes. There's integration testing, which is testing a bunch of classes working together, and system testing, which is testing the whole thing, which is every class, every function, all put together in like a production-like environment. We usually have, like for a website, for example, you have a production server, which is where the actual already tested version runs, and then there's a test server, which is probably the next version that you're getting ready to release. And you push the finalized version onto the test server, and you have the quality assurance people try it out for a couple of months. And if they're not able to find any problems, then you release it to the production server and your customers can access it. But if they find bugs, they'll submit a bug report to some bug reporting software, and you'll get some kind of a notice, maybe integrated with your GitHub or something like that. That'll create an issue saying, you got to fix this. This is what it is, and it'll describe what you need to do in order to fix that error. So those are the main types of functional tests. There are also some non-functional tests. We're not really going to talk about those in this class, but you'll learn about them in other classes. So performance testing is one of them, sometimes called load testing. typically used on things like websites or mobile apps or whatever, where just want to make sure that it can handle significant load. So as an example, a website, you might run a bot to connect to it like 10,000 times and perform a request, 10,000 simultaneous requests, and see if that breaks your app. You might do some security testing to see if you're doing something specifically malicious, like cross-site scripting or something like that, to see if your application is vulnerable to those sorts of things. Usability testing, you'll get some people to come in and see how easy it is to use the software, and then you might survey them after, and they might say, oh, well, I was able to figure out how to use this, but this one took me a little while to get used to. And there also is the user experience testing, where sometimes you can ask them how they felt about the user interface. Did it make them tense and nervous, or did it make them feel comfortable and at ease? All this sort of stuff is really important, obviously, for software development. There's also localization testing, which I have a lot of personal experience with, because I used to work for a company that was based in North America, but our primary customer was in Japan, and so we had to, and few of us at the company spoke Japanese, so we had some people from Japan fly out and work in our office, and then we also would then submit a version to a Japanese company whose primary job was to test to make sure, and they would investigate every nook and cranny of the application to make sure that it was functioning correctly and everything was used correctly in context. So you want to make sure that the right translations are being used, because if you just pass a word to a translation service, words can mean different things in different contexts, and maybe you meant the word okay made sense to you, so you put the word okay in some document, and they translated the word okay into Japanese and sent it back to you. But in the context of it being an okay button, maybe that didn't make any sense. Back in those days, and maybe I'm remembering this wrong because it was a super long time ago, I remember a story about we sent off an application that worked exactly that way. We had an okay and cancel button on a lot of our pop-up windows on our website. And there were actually pop-up windows, but you know what I mean. And it turns out that, according to our localization testers, that in Japan it was common to just actually use the English word okay. The cancel would be in Japanese, but okay was written in English. For whatever reason, they were just used to that. And so when we translated it to Japanese, there is a translation, okay, to Japanese, but it looked strange to them and it didn't quite feel right. So they made us change it back to English. So that was a really good thing that we did a lot of testing for that. Okay, so the one that we care about, though, is unit tests. So we're going to do some tests. There are frameworks for pretty much every programming language to make this much easier. You don't really need a framework. In fact, it's kind of the whole idea of test-driven development, which is when you write the test first and then you write the code that makes the test pass. So like what you'll do is you'll write a test that tests to make sure your functionality works, which of course is going to fail because you haven't written the functionality yet. And then after you finish the functionality, hopefully the test passes, but you run the test anyway just to make sure that it passes. Well, there's a book called Test-Driven Development by Kent Beck, which introduced the concept to the world. And in the course of the book, Kent Beck actually wrote a framework for making unit testing much easier for Java specifically, I think it was, if I remember correctly anyway. And since then, a lot of other programming languages have kind of created a very similar framework just to make it as convenient as possible. So anyway, there is one for Python called Unit Test. There's lots of unit testing frameworks for other languages like JUnit for Java, NUnit for .NET languages like C#, Boost Test for C++, and so on. And these might be kind of out of date because I tend not to use Java and C# that much anymore, except in game dev I use C#, but I don't tend to use unit testing in those languages anymore. So these are probably out of date, and there's probably something much, much better now. But anyway, what you do is you write a bunch of tests in this unit testing framework, and each test is going to test one thing. Maybe it tests a function, maybe it tests a class, and it does so through a number of assertions. And basically what an assert is, some programming languages actually have an assert statement. And basically what it is you're saying, if this thing is true, then don't do anything. But if it's not true, I want you to crash the application. Like I want you to generate a runtime error and stop the application. because basically this is something that absolutely has to be true for a program to be correct. And so maybe having a dedicated construct to this isn't really necessary. That's why these unit testing frameworks exist, because they provide functions that basically do the same thing. They'll throw an exception or something like that if the assertion fails, or maybe they'll just kind of keep note of how many of the assertions failed, and then at the end they'll show you a report of how many tests passed and how many didn't. Okay, so we're going to use the unit test one. So basically what we're going to do is we're going to create a class. All unit testing in the unit test library uses classes. So I'm going to call this pet test, and it inherits from the test case class that's in the unit test library. So you can see I've inherited it there. And then what happens basically is when I execute this code, it's going to execute every function that has test underscore as its prefix. So you can see I do only have one function here that says test underscore speak. So presumably there is a function. There's a class called pet, and that pet class has a function called speak. Because you can see here in this function here, I create a new pet. I pass it a couple of things. This is probably like, what species is it? It's a cat. And what's the pet's name? Whiskers. And then what we do is we call pet1.speak, and presumably that returns something that the animal says, and then it compares it to this. So this particular function says, I want to assert that these two be equal. So if these two are not equal, then this is going to be a failed assertion. If they are equal, kind of nothing happens. But if they aren't equal, then it actually will show up in your report, and it'll say, hey, this one in particular failed. And it'll say, pet1.speak value was meow, no exclamation mark, and it was supposed to be meow with an exclamation mark. So you can go back and change your program and make sure that it matches up exactly. Here's another test. I'm just doing something different just to show you a different assert, but I'd probably be consistent about it. But here I create another pet, which is a dog, and the dog's name is Spike. But in this case, instead of doing assert equal, I say assert true. Assert true only takes one argument, and that argument has to be true. And so I'm going to use a Boolean expression here, which should evaluate to true. If it doesn't evaluate to true, then this assert is going to fail, just like the assert equals fails if the two values aren't equal. All right. There are also versions of these functions that can also take a string argument that will be a helpful error message that I'll print out in the summary. When you're looking at the end, when you're seeing which tests passed and which ones didn't, then you can look at the summary and see those extra error messages to give you a clue of specifically which assertion failed. So for example, if I'm testing the speak on a cat, I might say, well, the cat output for speak was incorrect and should be this. So that can be helpful. That's not what I've used here. I usually find that this is sufficient for me to figure out exactly what went wrong. But anyway, the other version is there if you want some more completeness. All right, anyway. So even though we covered 3 topics today, those were all pretty easy. So we learned some simple topics today, but these are actually very useful. I will also say that some of the knowledge that we learned from the file input and output is going to transfer very well to you learning other types of input and output. So input and output between 2 programs on the same system, or between 2 different programs across a network or the internet. The process is going to be quite similar. You're going to read data, you're going to write data. There is the possibility of binary reading and writing, but it's pretty analogous to reading and writing strings. And you'll have to know exceptions for that. But as your program starts to get more complex, you're going to have multiple classes, and those classes are going to be interacting in different ways. It's becoming more important to write unit tests. So out in industry, you're probably going to write unit tests, probably not for every line of code that you write, but for some of the most important code in the program that you're working on, you're going to have some unit tests to make sure that that code is behaving exactly as expected. So you might have some user interface code, you're generating some JavaScript or whatever to check to make sure that the email address that the user typed in that text box is correct. You may or may not unit test that, but the functionality that takes that email address and stores it when it's creating a new user, that'll probably be thoroughly tested, and you can use a unit testing framework in order to do that. So anyway, a really simple and short lecture. So I'll see you next time. Take care now.